our continuing video, we will look at the area of composite shapes today. We will learn to understand what a composite shape is, to identify the simple shapes that make up a composite shape, and to then find the area of those composite shapes. And as always, we'll know that we can do this when we can, in fact, identify the composite shape. We can identify the shapes, the simple shapes that make up that shape, and also find the area. The key ideas: composite shapes are those that are made up of more than one simple shape. The area of a composite shape can be found by either adding or subtracting the areas of the simple shapes. So for example, in this first one here, we have a square plus a triangle, and we can see the separation of the two by the red dotted line. And we would find the area of that one by finding the area of the square shape and then of the triangle and adding them together. So that would be an additive process. The second one, we can see that we have a rectangle with a corner missing. So that corner is a triangular shape shown by the dotted red line. And we could find the area of that triangle and the area of the larger rectangle. And then to find the area of just that rectangular composite shape, we could take the smaller triangle away. So that would be a subtractive process. And sometimes they may contain both steps. So here we have some examples. If we look at the first one on the left-hand side, we might see this as a rectangle with a triangle cut out. So the cut out triangle might be this part along here. Okay. Or we could also see it as a rectangle with an added triangle. So we might have this shape here and have this rectangle and this triangle here. So depending on how you wanted to go about this, or it may depend on what measurements you can find or already provided. In the middle example, we have the same situation. You could look at this as a sort of square looking shape with a triangle missing from the side here. Or you might see it again as a rectangle with a triangle. So here's the rectangle, here's the triangle there. So again, depending on how you see it, what measurements you have or what measurements you can easily find, you may do this as an additive or a subtractive. The third one's a little bit trickier. Again, if we look at it overall, it seems to be a larger rectangle. And then we probably have a triangle and a rectangle making up the small one. So we could see it that way. Or again, we might see it as a rectangle here and a triangle here. So again, it could be an additive or a subtractive process depending on which values we have, which measurements we have, or which are easy for us to find. So the point of this, I guess, is that often we might be able to see a composite shape in different ways. Usually you look for the easiest option, the one that requires the least amount of steps, the least amount of calculations. So here's some working examples. So the one on the left-hand side, we have this sort of L on its side, and in this case, it's been made up of a square up the top, so we'll call this the square, and we've got a rectangle down the bottom. And with the measurements that we have there, we do have everything we need to solve this. And again, on the right-hand example, similar to what we saw before, we have a rectangle with a triangle at the top, and we have all the measurements that we need to solve that as well. So let's go ahead and solve this. So let's start with the rectangle in the left-hand example. So the area of the rectangle, I'm going to show that like that. It is always good to label each of the parts of the composite shape. We know that the area of a rectangle is its length multiplied by its width. So the length in this case, I'll write that down, is equal to 3. And its width will be equal to 1 on the side here, which means, of course, that is equal to 3 centimeters squared. The area of the square, the small square up the top, well, we can see by the fact that it's got these markings in here that it is a square, definitely, because the sides are the same, and it's going to be a 1 centimeter length and 1 centimeter width. But the area of a square, though, is equal to length squared, remember? All right, which in this case is equal to 1. Now, don't confuse this is an L, so I might just draw that a bit differently. This is a 1 squared, which of course is equal to 1, and that's centimeters squared as well. And then the area total, I'm going to call it T, is equal to area of R plus the area of the S, which is equal to 3 plus 1, which is equal to 4 centimeters squared. So we had the area of the rectangle being 3 centimeters squared, the area of the little square being 1 centimeter squared, and of course those together, in this case we did an additive process, gave us a total of 4 centimeters squared. Let's turn our attention to the second one. So let's start this one as a rectangle, all right, and then we're going to have a triangle here. So the rectangle is going to include everything. So the area of the rectangle is equal to length times width, which of course is equal to 13, we'll say, make this the length, multiplied by width. Now the width is going to be the 4 that we know here, plus the 4 of this triangle. So we're having the full side down here, so it's going to be 8. So that, of course, is equal to 104, which, of course, is meters squared. Okay. Now, the area of the triangle, if we remember, that is half of the length times the height. Okay. Our height will be this 4 here. Right, we've got a right angle in the corner here. The height must be straight up from perpendicular to the vertex, remember? All right, so we've got a half multiplied by the length, we'll say, is 5, and the height, we'll say, is 4, which is equal to a half times 20, which is equal to 10 meters squared in this case. Okay? So what we have at the moment is the area for the full rectangle, including that triangle, and then we have the amount for just that triangle. So in this case, the area of total is equal to the area of the rectangle minus the area of the triangle, because we want to cut it off, which means it's equal to 104 minus 10, which makes it 94 meters squared. So the first one, we did an additive process. The second one, we did a subtractive process. We possibly could have done it differently, but with the examples and the information we had, it was much easier to do it the way we did instead of trying to break up these shapes differently, which we could have done, but we already had all the information we needed to go ahead in this particular format. So again, composite shapes rely on you knowing the area of rectangles, of triangles, and so forth, and going from there. Okay, so it's very important that you have understood all the area work that we've done up until now. Let's now have a look at the questions. Question 2 says to find the area of these composite shapes by adding together the area of the simpler shapes. Assume that all angles that look like right angles are in fact right angles. So this question has specifically told us to do an additive process, so we have to make sure that that is what we do. Again, you may be able to see that you could do it with a subtractive process, and you definitely could, but the question has specifically said by adding together, so we've got to make sure that we follow the question. So the first one over here, we can see then we have a rectangle, it looks like, and we have a triangle here. So let's work out the area of the rectangle first. So again, you can see I'm labeling everything. So area of the rectangle is length times width, which in this case is going to be 7 times 5, which is 35 meters squared. The area of the triangle is equal to half of the length times the height, which is equal to half of, let's say, length is 7. That's the same as the bottom of our rectangle, times the height, which is that 4 that they provided us, which is equal to half times 28, which is 14 meters squared then. And then area total. Now, I've done total there because if I just said area T, it's going to conflict with the area for the triangle that I did. So I might need to choose some better names in the future. But the area of the total shape is going to be equal to the area of the rectangle plus the area of the triangle, which in this case is 35 plus 14, which is equal to 49. Don't forget the meters squared unit in this case. Now we're going to do exactly the same thing with the second shape, but here they haven't given us all the information, or at least it looks like they haven't. First thing we're going to need to do is work out how we're going to break this shape up. So I'm going to break it up in a similar way to be a right angle triangle and a rectangle. Now, what are the measurements that I don't have? I have my height of my my triangle because it's the same as this line over here. So that's going to be 4 meters. What I don't have is my base measurement for my triangle. Okay, it's going to be my base here because there is my right angle. But I have the information I need. I know that this full length along the bottom is 10, and I know that this length across here is 6. So obviously what's missing if this was a full rectangle, for example, okay, this line here would be the same as this line here. So that must mean it's 10 minus 6, which means this is also equal to 4 meters. So I do have all the numbers I need. They just weren't given to me at the start. So let's go ahead and do this again. Area of the rectangle, sorry, let's just label them R1, and I'm going to call this T1 to differentiate it. So area of R1 is equal to length times width, which is equal to, let's go with, 6 times 4, which is equal to 24 meters squared. Area of triangle 1, that's what we've labelled it this time, is equal to half of length times height, which is equal to half of, oops, I forgot to multiply, half of length being 4, we said, and height being 4, which is equal to half of 16, which of course is 8 meters squared. And we'll say area T for total now, because we call the other one T1, is equal to area of R1 plus the area of T1, which of course is now equal to 24 plus 8, which is equal to 32 meters squared, not forgetting a unit. So again, we've done those with an additive process by looking at what the simpler shapes were, working out their individual areas, and then adding them together. Question 3 says to use subtraction this time to find the area of the composite shapes. Assume that all angles that look like right angles are again right angles. So again, this time we've been specifically told to use subtraction, so we have to make sure that that's what we do. So in our first one on the left-hand side, we have what looks like a square, or not quite a square actually, because one measurement is 8 and one measurement is 7, so it's actually a rectangle with a small right-angled triangle cut out from the side. So let's call this rectangle R1 and T1 for triangle 1, and let's work out their individual areas. So area of R1 is equal to length times width, which is equal to, we'll go 8 times 7, which is 56 meters squared. And the area of T1, the triangle, is equal to half of length times height, which is equal to half of the length, we'll say, is 4, and the height is 3, which means it's half of 12, which equals 6 meters squared. Okay, so we have the area for the rectangle, the full rectangle, and the area for the little triangle. Now, area total, we'll just call it area T, is equal to area of R1 minus, in this case, the area of T1, which in this case is equal to 56 minus 6, which means it's 50 meters squared. So the area of the shape in blue, the rectangle minus that triangular red part, is 50 meters squared. In our second example, again, we need to look carefully at this. We have a triangle. It does look like it's a right angle triangle. Here is our right angle up in what is actually the top at the moment. And it has what looks to be a square cut out of it. So we know it is a square because we've been told at least 3 of these sides are all the same as each other. So 3 sides of something that's rectangular in shape are the same. Well, this fourth missing side would also be the same. It has to be. All right, so we've got a square cut out. So let's call this T1, and I'll call this S1 for square 1. Okay, let's start by looking at the triangle. We have one measurement here being 6 meters. We'll call this our base. And our height is provided here at 3.5. Now, think about if we drew a dotted line down from this vertex, so this vertex up here, down to this base, there would be our right angle, so that our height is actually at a right angle, so is perpendicular, that's the term we need to use, to our base, and it goes to a vertex. All right, so that measurement's actually given over here as 3.5 meters. So we have our base and our height that we need to find the area of a triangle. So the area of T1 that we're nominating as a triangle is equal to half of our base times our height, which in this case is equal to half of base we're saying is 6, multiplied by height, which we're saying is 3.5, which in that case is equal to half of 21, which is equal to 10.5 meters squared. So that is the area of our triangle. Now the area of the square, we've got a square and we know that the side that's given is 2 meters, and obviously being a square all sides are the same. So the area of square 1, we're calling it, is equal to the length squared. So again, that's an L, not a 1, which in this case is equal to 2 squared, which of course is 4 meters squared for the area. And because this is a subtractive process, our area total is equal to the area of the triangle minus the area of the square, which in this case is equal to 10.5 minus 4, which is equal to 6.5 meters squared. So we started by finding the bigger triangle shape and then removing from it the area of the small square. Question 4 says, find the areas of these composite shapes. Assume that all angles that look like right angles are in fact right angles. So we need to look at this shape carefully. First of all, we might be tempted to draw a dotted line across here and make this into a triangle. But what we'll quickly see is that it actually doesn't join up with anything that's useful. We could maybe find that triangle, but then we've got this weird shape through here that's not very easy to find. So there might be a better way to do this. Let's instead consider that this is a big rectangle that comes across like this, including this bottom bit, and then let's take out this shape and possibly this shape here, this triangle. So can we work out the measurements that we need for that? Let's have a closer look. So let's see if we can work out the big rectangle first. So the rectangle is going to be 9 meters tall. We've got that size, and we've got a 5 meter down here now. We know that this also must be 5 meters because it's got the symbol, and this unknown, this dotted line we've drawn in, must also be 5 because it would be the same as this one here, and that's also got the same symbol. So we must have 5 across there as well, which means that the total across this base, if you like, or this width, is going to be 15 meters. So that's that total measurement right across. Okay, so it's good to know that. So the area of the rectangle, let's just call it that, is equal to length times width, which is going to be 15 for the length, let's say, multiplied by 9, which is going to be 135 meters squared. Okay, so we know what that big rectangle is. Now, the easy shape we've got is this one here. This is going to be S1. This is a square that we're going to cut out. And again, we already know that it's going to be 5 meters across because we've just worked that out from earlier. So the area of the square is going to be the length squared, which is going to be 5 squared, which is going to be 25 meters squared. So we've got that area. Now we need to find the area of this triangle here. We'll call it T1. Now, how do we go about finding that? We know what this length across the top here, so we'll call this its base is going to be. That's going to be the same as this 15 at the bottom, so that's going to be 15. And we can work out this measurement here, which will be the height, because we know that the part underneath it is 6. And we know that the opposite side is 9 in total. That would have to be the same as this full length. So height is going to be 9 minus 6, which means it's going to be 3 meters. So this space is going to be 3. So we can now find the area of triangle 1 as being half of the length times the height, which is half of length we said is 15 times the height of 3, which is equal to half of 30, 45, which is equal to 22.5 meters squared. So we've now got the three shapes, if you like, that make this up. We've got the big rectangle, we've got the small obvious square that's been cut out, and we've got this extra triangle that we've technically added in at the moment that we need to take back out. So the area of total, so the total area is going to be equal to what we have called area of the rectangle, the big rectangle, minus the area of square 1, and also minus the area of triangle 1. Okay, so we have at the moment 135 minus the square 1, which we said was 25, minus the triangle, which is 22.5. So let's just do those one at a time. So 135 minus, we'll go to 25 first, is 110, still minus a 22.5, and then it's equal to 87.5 meters squared. So the area of the shape that was originally drawn is equal to the area of the big rectangle minus the small square minus the small triangle, which becomes 87.5 meters squared. Now question 5 says, by finding the missing lengths first, calculate the area of these composite shapes. So we have this cross-looking thing, which obviously has all sorts of sides being the same because there's lots of those little dashes indicating that all of those edges are the same, and they've also indicated some right angles for us. So what we have is one measurement given of 15 meters. That's right across. So that means this side here plus this side here plus this side here, if they were all drawn together, would have to be equal to 15. So there are three sides, so each of those must be equal to 5 because the total length of 15 divided by the three lines that make that up, which means each of these sides is a 5. All right, and because it's actually said all of the sides are the same because of those little dash lines on there, it means absolutely every side here is 5 meters in length. Now, what does that help us with? We could go about this in two ways as far as I can see. Well, there's actually a few more than that, but two main ways. The first way might be to look at this as being one big square. So we might actually continue this square all the way around. So one big square of 15 by 15, and then take away 4 little squares from it. That's one option. Another option might be to look at them instead as individual squares. So there'd be one square there, 2 squares, 3 squares here, 4 squares with this one here. So square 1, square 2, square 3, square 4. But there'll also be this square in the middle, which we'll call square 5. So we could work out what one square is, and because we know they're all the same, we could multiply that by 5. Both of those would be correct, but I'm going to go with option 2 because I think that's going to be a little bit quicker. So let me just quickly rub out all that mess and let's have a look at that again. Okay, so what I've decided to do is to divide this up into the squares. So here I have one square, which we'll call square 1, square 2, square 3, square 4, and of course the middle one we'll call square 5 just because I did it last. Okay, so I'm going to say the area total is equal to square 1 plus square 2 plus square 3 plus square 4 plus square 5. I should have really said area of each of those, but anyway. Now, because we know that all of these squares are going to be the same, we could also just say is going to be equal to 5 times square 1, for example. Okay, because we've got 5 squares that are all going to be the same, so that would also be correct. Let's start by working out one square. So that's the area of square 1 is equal to the length times the width, which of course is equal to 5 times 5, as we've already said, which is equal to 25 meters squared. Now we could do that for each of them, area square 1 plus area square 2, etc. But we've also worked out that we can just say 5 times because all these squares are the same. So that would then equal to, I'm just going to do it on the side for the space because I'm going to bump into that equation. We would say 5 times 25, which of course would be 125, and we would put meters squared there. So it looked like a fairly complicated shape to begin with, but in the end, it wasn't that hard. If we wanted to go about it the other way, we'd still probably do the same thing. We would find out the area of the big rectangle. In fact, let's do it really quickly. The area of the square B, we'll call it the big square that goes all around, would be equal to 15 times 15, which of course is equal to 225. Then we would still have to work out the area of one square. So let's just say square 1, which would now be this corner square though. And that would still be 25 metres. We know that from down here. We won't bother doing the math again. But now we'd have to say the area total is equal to the area of the big square minus 4 times the small square. All right, which would then be 225 minus 4 times 25, which of course will be equal to 225, minus 100, equal to 125 meters squared. And you can see we've gotten the same answer. But I think that was a little bit more complex because we still had to work out the big square and the small square, and then we had to do a multiplication of the small square as well. So I actually think there was more steps involved with that one instead of simply saying find one square and multiply it by 5. So I guess the point of this question is sometimes it may look simple, it may take more work than you believe, and sometimes there are just better ways to go about it. And it's just with a bit of practice and with a bit of knowledge, I guess, that you start to see quicker ways to do things, simpler ways of maybe doing the same question. Question 6. A wall has 3 square holes cut into it to allow for windows, as shown in the picture that we've been given. Find the remaining area of the wall. So it wants to know everything without those areas cut out. So again, we can see we have a big rectangle shown by the green, and we have 3 small squares that must all be the same size because each of those sides has got a little dash on it, indicating they're all equal, and we've been given one measurement. So let's work out the area of square 1 and the area of rectangle 1. So the area of rectangle 1 is equal to length times width, which is equal to 4.1 times 8, which is equal to 32.8 metres squared. So that's the full rectangle, but now we need to take away 3 of those windows actually. So the area of square 1 is equal to 1.5 squared because we know all the measurements are the same, which is going to be equal to 2.25. Oh, sorry, meters squared, don't forget. But there are 3 of those. So let's do a formula for the whole thing. So the area of the total space that we need is equal to the area of rectangle 1 minus 3 times the area of square 1, which is equal to, let's put the numbers in, 32.8 minus 3 times 2.25. Let's do just the bracket first, 32.8 minus 3 times 3.25 is 9.75. And then we do that last part, 32.8 minus 9.75 is equal to 23.05 meters squared. So we find the area of the big rectangle, we found the area of one of those windows, and because we can clearly see that each of the windows is the same, we could do some multiplication of that area and then take that from the big area. Again, we could have sit there and worked out the 3 individual windows, but that's where the knowledge and the thinking comes in to go, hey, save yourself some time. There's a multiplication I can do there. Question 8, it says to explain why using subtraction is sometimes quicker than using addition to find the area of a composite shape, and it gives you a diagram to refer to. Now, I can't really show you an answer to this because this is really about your understanding, but I will suggest you to think back to some of the questions that we did and to look at this shape really. So how would you break this up so that you have shapes that you can add together, and how would you break it up into ways that you have shapes that you can subtract? And really, I think it would come down to how many shapes would you have to add up, and how many shapes would you have to subtract? And if you can look at that, you might be able to see a reasonable answer for this question. And that is the end of the questions for today. So as always, go back and rewatch these. I know sometimes they can get a bit messy. It's really about, in this case, looking at your shape carefully. How can you break it up? Identifying the measurements for the sides that you may not be given so obviously. It's always good to draw diagrams if they're not provided. It's always great to label things. Please label each of the small shapes that you create so that you can keep track of all your different pieces. And yeah, really just go through it. If you've got questions, as always, please get in touch.